Gaseous oxygen-enhanced ignition and combustion damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of gaseous oxygen-enhanced ignition and combustion damage based on API 571. Many metals are flammable in oxygen and enriched air, greater than 25% oxygen, surfaces even at low pressures, whereas they are non-flammable in air. The spontaneous ignition or combustion of metallic and nonmetallic components can result in fires and explosions in certain oxygen-enriched gaseous environments if not properly designed, operated, and maintained. Once ignited, metals and nonmetals burn more vigorously with higher oxygen purity, pressure, and temperature. Gaseous oxygen-enhanced ignition and combustion damage refers to the potential hazards and destructive effects that occur as a result of increasing the concentration of oxygen in the combustion environment. This process can significantly alter the behavior of ignition and combustion reactions, leading to various forms of damage across different materials and environments. Description of gaseous oxygen-enhanced ignition and combustion damage. Number 1 is mechanism of action. In normal atmospheric conditions, air comprises about 21% oxygen. When the concentration of oxygen is increased, combustion reactions can occur more rapidly and violently due to the higher oxidation potential. This can lead to accelerated burn rates and enhanced energy release during combustion. Number 2 is types of damage, includes. Number A of types of damage is thermal damage. Increased oxygen levels elevate combustion temperatures, which can lead to thermal degradation of materials such as metals, plastics, and composites. Prolonged exposure to higher temperatures can cause warping, melting, or structural failure. Number B of types of damage is corrosive damage. The higher combustion temperatures can also produce corrosive byproducts that may degrade materials over time, accelerating oxidation processes that compromise structural integrity. Number C of types of damage is mechanical damage. If materials are subjected to rapid pressure changes due to explosive combustion, mechanical damage can ensue. This includes shrapnel effects, structural collapse, or fragmentation of components. Number D of types of damage is fireball and blast damage. In high-pressure environments, enhanced oxygen levels can lead to violent ignition events characterized by fireballs and blasts that can cause extensive physical damage to nearby structures and materials. Number 3 is applications and risks. While gaseous oxygen-enhanced combustion can be harnessed for specific applications, such as in certain industrial processes or rocket propulsion systems, it also poses significant risks. In confined spaces or environments with combustible materials, the probability of catastrophic failure increases dramatically due to the rapid spread of fire and explosion potential. Number 4 is preventive measures. To mitigate the risks associated with oxygen-enhanced combustion, careful control of oxygen concentrations is essential. Engineering controls, safety protocols, and appropriate material selection are vital to reducing the likelihood of ignition and controlling the effects of combustion damage. Number 5 is impact on safety standards. The presence of oxygen-enriched atmospheres necessitates stricter safety standards and protocols in industrial settings. Organizations must implement rigorous training and equipment standards to protect against the specific hazards associated with high oxygen environments. In summary, gaseous oxygen-enhanced ignition and combustion damage pose significant threats in various contexts, demanding careful consideration in design, operation, and safety measures to prevent catastrophic incidents and material failure. Gaseous oxygen-enhanced ignition and combustion affected materials based on API 571. Number A, carbon steels and low alloy steels are flammable in low-pressure oxygen, greater than about 15 sig, 0.103 MPa. With special precautions, these materials are safely used in high-pressure oxygen. Number B, austenitic stainless steels, 300 series, have better resistance to low-pressure oxygen and are generally difficult to ignite at pressures below about 200 sig, 1.38 MPa. Number C, copper alloys, with greater than 55% copper, and nickel alloys, with greater than 50% nickel, are very fire-resistant and are generally considered non-flammable. Because of their excellent oxygen compatibility, they are often selected for impingement and turbulent services such as valves and instrumentation. See Figure 469, burn-through of a PTFE-line stainless steel hose in high-pressure gaseous oxygen, or GOX, service. Grease contamination ignited and penetrated the hose. Alloy 400 is highly resistant. Number D, although widely used for oxygen cylinders and in oxygen manufacturing plants, aluminum is usually avoided for flowing oxygen. If ignited, it burns quickly and with a large energy release. Number E, the easiest materials to ignite are plastics, rubbers, and hydrocarbon lubricants, and these are minimized in oxygen systems. Number F, titanium alloys are generally avoided in oxygen-enriched service because they have low ignition energies and release a large amount of energy during combustion. Tests indicate that titanium can sustain combustion at oxygen pressure as low as 7 kPa, 1 psi, absolute. Most industry documents caution against the use of titanium in oxygen systems, references 6 and 7. Note, these are general guidelines and should not be considered for design. Gaseous oxygen-enhanced ignition and combustion can significantly impact various materials due to the increased reactivity and combustion temperatures associated with higher oxygen concentrations. Here are some categories of materials that can be affected. Number 1 is metals, includes. Number A, of metals is aluminum. It can oxidize rapidly, leading to increased oxidation rates and potential structural failure. Number B, of metals is steel and alloys. High-temperature environments may accelerate oxidation, especially at weld seams and heat-affected zones. Number C, of metals is titanium, highly reactive in elevated oxygen environments, which can lead to ignition at lower temperatures than in air. Number D, of metals is copper, while more resistant, can still suffer from accelerated oxidation and embrittlement. Number 2 of categories of materials that can be affected is polymers, includes. Number A, of polymers, is many polymers, like PVC, PTFE, and various thermoplastics, can degrade or combust more readily in oxygen-rich environments. Number B, of polymers is certain elastomers may also lose their mechanical properties due to oxidative degradation. Number 3 of categories of materials that can be affected is composites, includes. Number A, of composites is fiber-reinforced composites can suffer from degradation of the matrix material, leading to loss of mechanical integrity. Number B, of composites is the fibers themselves may be less affected, but matrix degradation can compromise overall strength. Number 4 of categories of materials that can be affected is ceramics. While generally more stable in high-temperature environments, certain ceramics might be ruined by thermal shock under rapid combustion conditions. Number 5 of categories of materials that can be affected is insulation materials. Various insulation materials, particularly organic ones, like fiberglass with polymer binders, can ignite and degrade quickly in high oxygen conditions. Number 6 of categories of materials that can be affected is coatings. Protective coatings may fail under high oxygen environments, leading to accelerated corrosion or degradation of the underlying material. Number 7 of categories of materials that can be affected is wood and other organic materials. Increased combustion rates can lead to rapid ignition and combustion of wood and other organic materials, presenting significant fire risks. Number 8 of categories of materials that can be affected is glass. While glass is generally stable, thermal shocks from high oxygen combustion environments might lead to cracking or other forms of glass failure. In summary, different materials exhibit varying degrees of susceptibility to damage from gaseous oxygen-enhanced ignition and combustion. Proper material selection, protective coatings, and environmental control are vital to mitigate these risks in applications where increased oxygen concentration is present. Gaseous oxygen-enhanced ignition and combustion critical factors based on API 571, Number A, many factors affect the likelihood of combustion and ignition in oxygen services including the system pressure, oxygen content of the stream, line velocity, component thickness, design and piping configuration, cleanliness and temperature. Number B, the primary concern under high-velocity oxygen flow conditions is the entrainment of particulate and their subsequent impingement on a surface, such as at a pipe bend. Oxygen velocities in carbon steel and stainless steel piping should comply with industry limits as shown in reference 1. Allowable velocity is a function of pressure and flow condition, direct impingement or non-impingement. Number C, the temperature of a material affects its flammability. As temperature increases, a lower amount of additional energy is required for ignition and sustained combustion. The minimum temperature at which a substance will support combustion, under a specific set of conditions, is referred to as the ignition temperature. Published ignition temperatures for most alloys are near the alloy's melting temperature. However, these are measured in non-flowing conditions. Actual systems can suffer ignition and combustion at room temperature, and lower, due to particle impact and other mechanisms. Number D, system cleanliness is important for the safe operation of oxygen systems. Contamination with metallic fines or hydrocarbons such as oils and greases during construction or maintenance activities can lead to fires during subsequent start-up of the unit. These materials are easy to ignite and can lead to a large fire and breach of the system. Number E, impingement areas such as sharp elbows, T's and valves have a higher risk of ignition than straight pipe. Particles in the flowing oxygen can strike these areas and cause ignition. Operation of valves and regulators, opening/closing, cause high turbulence and impingement, and only components selected and cleaned specifically for oxygen service should be used. Gaseous oxygen-enhanced ignition and combustion involves the use of oxygen at levels higher than atmospheric concentration to facilitate or improve the ignition and combustion process. This phenomenon is particularly significant in various industrial applications, including aerospace propulsion, chemical manufacturing, and energy production. The critical factors influencing gaseous oxygen-enhanced ignition and combustion damage can be categorized as follows. Number 1 is oxygen concentration, includes. Number A, of oxygen concentration is oxygen levels. The increase in oxygen concentration can lead to faster ignition and combustion rates. Higher concentrations can also cause more severe thermal and pressure effects, potentially leading to material damage. Number B, of oxygen concentration is oxygen enrichment. Understanding the thresholds for safe operation versus hazardous conditions is critical, as small increases in oxygen can lead to significant changes in combustion dynamics. Category number 2 of the critical factors influencing gaseous oxygen-enhanced ignition and combustion damage is flame temperature, includes. Number A, of flame temperature is combustion temperature. The use of pure oxygen can result in higher flame temperatures, which may exceed the material limits of combustion chamber components, leading to thermal damage. Number B, of flame temperature is heat transfer. Enhanced heat transfer characteristics due to increased combustion temperatures can lead to overheating of materials. Category number 3 of the critical factors influencing gaseous oxygen-enhanced ignition and combustion damage is material properties, includes. Number A, of material properties is thermal stability. Materials used in oxygen-rich environments need to have high thermal stability to withstand elevated temperatures. Number B, of material properties is corrosion resistance. Oxygen can promote oxidation and corrosion in materials, which is crucial for long-term integrity. Number C, of material properties is mechanical properties. Changes in material strength and toughness, especially in high-temperature environments, can lead to structural failure. Category number 4 of the critical factors influencing gaseous oxygen-enhanced ignition and combustion is combustion products, includes. Number A, of combustion products is toxicity and reactivity. The products of combustion in oxygen-rich environments can be more aggressive, producing compounds that may contribute to damage, e.g., increased concentrations of NOx. Number B, of combustion products is soot formation. Reduced soot formation can occur in high oxygen environments, but incomplete combustion can yield different forms of damage or deposits. Category number 5 of the critical factors influencing gaseous oxygen-enhanced ignition and combustion damage is ignition dynamics, includes. Number A, of ignition dynamics is ignition delay time. The time required for ignition may be significantly reduced in the presence of high oxygen concentrations, affecting design considerations for ignition systems. Number B, of ignition dynamics is ignition sources. The selection of ignition sources must be critically evaluated since enhanced combustion can lead to rapid propagation and damage. Category number 6 of the critical factors influencing gaseous oxygen-enhanced ignition and combustion damage is combustor design, includes. Number A, of combustor design is geometry and flow. The design of combustion chambers and injectors must accommodate the altered flow characteristics caused by the higher reactivity of oxygen-enriched mixtures. Number B, of combustor design is cooling systems. Enhanced cooling mechanisms may be required to prevent damage from elevated heat loads. Category number 7 of the critical factors influencing gaseous oxygen-enhanced ignition and combustion damage is safety protocols, includes. Number A, of safety protocols is handling and storage. Careful procedures must be established for the safe handling and storage of oxygen to avoid catastrophic failure due to fire or explosion. Number B, of safety protocols is monitoring and control systems. Real-time monitoring of oxygen levels and combustion dynamics is needed to mitigate risks. Category number 8 of the critical factors influencing gaseous oxygen-enhanced ignition and combustion damage is operational conditions, includes. Number A, of operational conditions is pressure effects. The behavior of oxygen-enriched combustion at varying pressures, including how pressure influences flame characteristics and material stress. Number B, of operational conditions is fuel composition. The type of fuel used interacts with the oxygen concentration, affecting combustion efficiency and damage potential. In gaseous oxygen-enhanced ignition and combustion scenarios, a comprehensive understanding of these critical factors is essential for ensuring safe and effective operation while minimizing the risk of damage to systems and components. Proper engineering design, material selection, and operational management are key to addressing the challenges posed by high oxygen concentrations in combustion processes. Affected units or equipment because of gaseous oxygen-enhanced ignition and combustion based on API 571, Number A, these guidelines apply to any unit that uses oxygen or enriched air for combustion or other process reasons. Number B, oxygen is sometimes used in sulfur recovery units, SRU, and fluid catalytic cracking units, FCCU, gasification, and partial oxidation, POX, units. See Figures 4:64, thermal combustor on the front end of a reaction furnace on a sulfur recovery unit. See Figures 4:65, same as figure above after damage due to oxygen combustion resulting from oxygen injection into the thermal combustor on the front end of the reaction furnace. See Figures 4:66, same as figure above when viewed from a different angle. Number C, oxygen piping systems especially valves, regulators, and other impingement areas are potentially vulnerable. Non-metals such as those used for seats and seals, are easier to ignite than metals, see Figure 4:69, burn-through of a PTFE-line stainless steel hose in high-pressure gaseous oxygen, GOX, service. Grease contamination ignited and penetrated the hose. Gaseous oxygen-enhanced ignition and combustion can significantly affect various units and equipment, particularly in industries that manage or utilize combustion processes. Here are some key areas and equipment that may be impacted. Number 1 is combustion engines, includes gas turbines, internal combustion engines, such as automotive engines, aircraft engines. Number 2 is furnaces and boilers, includes industrial boilers, heating furnaces, recycling and waste incinerators. Number 3 is gas handling equipment, includes oxygen compressors, storage tanks, piping systems. Number 4 is propellants and rocket engines, includes liquid rocket engines, solid propellant burners, ignition systems. Number 5 is chemical processing equipment, includes reactors that utilize combustion processes, catalytic converters. Number 6 is safety systems, includes ventilation systems, fire suppression systems. Number 7 is materials and structural components, includes reactor walls and furnace linings, pipelines, and tanks susceptible to embrittlement or oxidation. Number 8 is control systems, includes monitoring and control instrumentation that may be affected by high temperatures or pressures. The use of oxygen-enriched atmospheres can lead to increased combustion rates, elevated flame temperatures, and potentially harsher operating conditions, which can result in accelerated wear, degradation, or damage to the above types of equipment. Proper design, material selection, and maintenance practices are essential to mitigating these risks. Appearance or morphology of gaseous oxygen-enhanced ignition and combustion based on API 571, Number A. In some cases, a small component will burn, such as a valve seat, without kindling other materials and without any outward sign of fire damage. It is noticed when the component is removed because it is not functioning properly. See Figure 4.67, photograph of a burned 304 SS elbow. The fire started in an upstream stainless steel wire filter, due to particle impact, and the burning filter material impacted the elbow and ignited it. Thin stainless steel components, such as filter, are much more flammable than thicker thin SS. Figure 4.68, photograph illustrating burn-through of a brass pressure gauge. Brass is generally suitable for oxygen service. However, the gauge was not intended for oxygen service and was not oil-free. Hydrocarbon contamination, probably from manufacture, caused the fire. Number B, also, external heat damage, glowing pipe or heat tint, is a strong indication of an internal fire. This can be caused by accumulation of flammable debris at a low point or other location in combustion or smoldering of the debris. Number C, the worst situation is when the pressure envelope is breached because of fire. Oxygen fires can cause significant burning of metal components and extensive structural damage. See Figure 4.68, photograph illustrating burn-through of a brass pressure gauge. Brass is generally suitable for oxygen service. However, the gauge was not intended for oxygen service and was not oil-free. Hydrocarbon contamination, probably from manufacture, caused the fire. Gaseous oxygen-enhanced ignition and combustion can significantly alter the morphology of the materials involved, particularly in combustion systems and environments where oxygen concentrations exceed those found in normal air, approximately 21% oxygen. Here are some key points related to the appearance and morphology of materials subjected to such conditions. Number 1 is color changes. Materials may display distinctive color changes due to oxidation. For example, metals may develop a layer of oxide, such as rust in iron or a shiny layer in aluminum, that can appear bluish, yellow, or gray. Number 2 is surface roughness and texture. Increased combustion efficiency can result in more aggressive reactions, leading to pitting, etching, or general surface roughness. The result may be a more porous appearance or a roughened surface, which is a sign of increased oxidation. Number 3 is deformation and distortion. High temperatures and pressures in oxygen-enriched environments can cause significant mechanical stress, leading to warping, melting, or other forms of physical deformation in structural materials, such as metals and plastics. Number 4 is soot and residue. In cases where combustion is incomplete or varied, you may find soot deposits and residues that can appear black and greasy. These residues can signify areas of incomplete combustion or localized hot spots where the reaction conditions were not uniform. Number 5 is cracking and spalling. Elevated oxygen concentrations can accelerate material degradation, potentially leading to cracking, spalling, or flaking off of surface layers. These features may appear as fine cracks or larger flakes breaking away from the substrate. Number 6 is interaction with fuel. Depending on the type of fuel being burned and its reaction with high concentrations of oxygen, the morphology can also show signs of reaction products like tar or other complexes, especially in hydrocarbons. Number 7 is deposition of combustion byproducts. Higher oxygen levels can lead to more complete combustion, which may result in different deposit patterns, often creating ash or other byproducts that can accumulate on surfaces. Number 8 is heat-affected zones. Materials adjacent to the combustion area may show heat-affected zones with gradients in color and structure, indicating varying degrees of thermal exposure. These morphological alterations are significant for industrial applications, safety assessments, and the understanding of material behavior under oxygen-enriched conditions. They can inform decisions about material selection, design of combustion systems, and the development of mitigation strategies for potential damage. Prevention and mitigation of gaseous oxygen-enhanced ignition and combustion based on API 571, refer to industry-recommended guidelines included in the references listed below. Some general considerations are as follows. Number A, oxygen fires are a sudden occurrence and not a progressive degradation or weakening of the material. Prevention is best accomplished by keeping systems clean, or cleaning them after maintenance or inspections. Number B, maintain velocity within recommended limits. If practical, avoid velocities that are nominally above 100 feet per second, 30 m/sec, in gaseous oxygen. Number C, ensure that replacement components are suitable for oxygen service. Number D, oxygen systems should be thoroughly cleaned after maintenance. Number E, minimize lubricants and use only oxygen-compatible lubricants. Number F, do not unnecessarily open oxygen systems for visual or other inspections as this could introduce contamination. Number G, a thorough review is needed before modifying oxygen systems to operate at higher pressures, temperatures, or velocities. Number H, minimize sudden changes in pressure in the system. If high-pressure oxygen suddenly enters a system initially at low pressure by quick operation of a valve, the dead end of that system experiences heating from adiabatic compression of the oxygen. Adiabatic compression heating can ignite plastics and rubbers, but will not ignite metals. Valve seats, seals, non-metallic hoses, etc., can be ignited by this mechanism. Number I, do not use plastic pipe in oxygen piping systems. Number J, personnel activities near oxygen piping and systems should be minimized during startups. Preventing or mitigating damage from gaseous oxygen-enhanced ignition and combustion involves several strategies, primarily focused on safety protocols, material selection, and engineering controls. Here are some effective measures. Number 1 is design and engineering controls, includes. Number A, of design and engineering controls is material selection. Use materials that are resistant to oxidation at elevated oxygen concentrations. Select metals, plastics, and composites that can withstand exposure to high oxygen environments. Number B, of design and engineering controls is containment systems. Design systems that can contain and manage oxygen-enriched atmospheres. This includes pressure relief devices and robust containment to prevent leaks. Number C, of design and engineering controls is ventilation. Implement adequate ventilation systems to manage the concentration of oxygen in the work area and reduce the risk of accidental ignition. Number 2 of prevention and mitigation effective measures is operational procedures, includes. Number A, of operational procedures is oxygen monitoring. Regularly monitor oxygen levels in areas where oxygen is present. Use sensors to detect and respond to elevated oxygen concentrations. Number B, of operational procedures is controlled atmosphere. Maintain controlled environments for processes involving oxygen to minimize risks. Limit the use of oxygen-enhanced processes to designated areas with proper controls. Number 3 of prevention and mitigation effective measures is equipment maintenance, includes. Number A, of equipment maintenance is regular inspections. Conduct regular inspections of equipment, especially those used to store, transport, or handle gaseous oxygen, to identify and mitigate wear and tear that could lead to leaks. Number B, of equipment maintenance is preventative maintenance. Implement a rigorous preventative maintenance schedule to ensure that all systems are functioning properly and safely. Number 4 of prevention and mitigation effective measures is training and safety protocols, includes. Number A, of training and safety protocols is employee training. provide comprehensive training for personnel on the hazards of oxygen-enriched environments and safe handling procedures for oxygen systems. Number B, of training and safety protocols is emergency response plans. Develop and practice emergency response plans for potential ignition or combustion incidents, ensuring that all employees know how to react in an emergency. Number 5 of prevention and mitigation effective measures is control of ignition sources, includes. Number A, of control of ignition sources is eliminate ignition sources, identify and eliminate potential ignition sources within areas where oxygen is present. This includes managing static electricity, hot surfaces, and electrical equipment. Number B, of control of ignition sources is non-sparking tools. Utilize non-sparking tools and equipment to prevent accidental ignition when working in oxygen-enhanced environments. Number 6 of prevention and mitigation effective measures is use of oxygen-rich workspaces, includes. Number A, of use of oxygen-rich workspaces is limit duration of exposure, minimize the time personnel spend in oxygen-enriched atmospheres. Use remote monitoring and control whenever possible. Number B, of use of oxygen-rich workspaces is segregation of processes, separate processes that involve combustible materials from those that use high concentrations of oxygen to reduce the risk of ignition. Number 7 of prevention and mitigation effective measures is fire protection systems, includes. Number A, of fire protection systems is active fire suppression systems. Install fire suppression systems specifically designed for oxygen-enhanced environments. These may include specialized fire extinguishing agents and systems that can quickly respond to combustion events. Number B, of fire protection systems is fire safety equipment. Ensure that appropriate fire safety equipment, including fire extinguishers rated for oxygen-enriched fires, is readily available and easily accessible. By implementing these prevention and mitigation strategies, the risks associated with gaseous oxygen-enhanced ignition and combustion can be significantly reduced. Organizations working with oxygen should always adhere to industry guidelines and regulations concerning oxygen safety. Inspection and monitoring for gaseous oxygen-enhanced ignition and combustion based on API 571, Number A, most commercial oxygen is dry and non-corrosive at normal ambient temperatures. Because of the sudden catastrophic ignition of metals under certain conditions, this type of damage is difficult to inspect for in advance. Number B, telltale signs of a minor fire such as external heat damage, or signs of malfunctioning valves or other components containing non-metallic components may be indicative of a problem. Number C, black lights can be used to check for hydrocarbon contamination. Inspection and monitoring of gaseous oxygen-enhanced ignition and combustion, OEIC, damage involve various methods that focus on assessing the integrity and safety of materials and systems exposed to high concentrations of oxygen during combustion processes. Here are some common methods used for this purpose. Number 1 is inspection methods, includes. Number A, of inspection methods is visual inspections, includes. The first of visual inspections is surface examination. Look for discoloration, melting, or signs of oxidation on materials. The second of visual inspections is crack detection. Identify cracks or fissures in materials that could be exacerbated by high oxygen environments. Number B, of inspection methods is non-destructive testing, or NDT, includes. The first of non-destructive testing, or NDT, is ultrasonic testing, or UT uses high-frequency sound waves to detect internal flaws or changes in material properties. The second of non-destructive testing, or NDT, is radiography. X-rays or gamma rays can be used to identify internal defects in materials exposed to high oxygen levels. The third of non-destructive testing, or NDT, is magnetic particle inspection, useful for detecting surface and near-surface discontinuities in ferromagnetic materials. The fourth of non-destructive testing, or NDT, is dye-penetrant testing, involves applying a dye to the surface, allowing for visualization of cracks and porosity when examined under ultraviolet light. Number C, of inspection methods is thermal imaging. Thermal cameras can detect hotspots and thermal stress points that may indicate underlying damage due to elevated temperatures associated with combustion. Number D, of inspection methods is scanning electron microscopy, or SEM, provides high-resolution imaging of surface morphology and can reveal oxidation patterns and microstructural changes caused by high oxygen levels. Number 2 of gaseous oxygen-enhanced ignition and combustion damage monitoring methods, includes. Number A, of monitoring methods is gas detection systems, continuous monitoring of oxygen levels in the environment with sensors capable of detecting elevated oxygen concentrations could help assess the risk of combustion-related issues. Number B, of monitoring methods is temperature monitoring, use of thermocouples and infrared sensors to monitor temperature fluctuations that could indicate combustion events or material degradation. Number C, of monitoring methods is pressure sensors, monitoring pressure changes within combustion systems can signal issues like leaks or integrity failure in containers that may be subjected to high oxygen levels. Number D, of monitoring methods is chemical analysis. Sample collection for laboratory analysis can help in assessing material degradation products or the presence of unwanted species formed during combustion. Number E, of monitoring methods is acoustic emission, monitoring sound waves generated by the rapid release of energy from material failure could serve as an early warning system for potential ignition hazards. Combining these methods provides a comprehensive approach to detecting gaseous oxygen-enhanced ignition and combustion damage. Regular inspections, monitoring, and appropriate safety measures are crucial for the safe operation of systems handling high concentrations of oxygen and for mitigating the risks associated with combustion processes. Thank you.